All right. What we're going to do is we're going to spend a few days and we're going to talk about gravity and then a few days on electrostatics. They actually sound like they're very different topics, and they kind of are, except that what we'll find is the equation for both the gravitational force and the electric force are very similar. And so we'll end up doing kind of some similarities and differences with them. We're going to start out with gravity for a couple of days. So let's get started with that. Yeah, that's all right. All right, so let's talk about gravity. What causes gravity? Okay, it's mass. Gravity is caused by mass. And it certainly is. The more mass something has, the more gravity it has. So if we're talking about the gravitational force between two objects, what do you think might be in that equation? Mass, for one thing. So, mass of what, though?
Gravity. Oh, wait.
The object, okay. So, we'll have the mass of the object there. And for right now, I'll just put it's proportional because as the mass gets bigger, the gravitational force gets bigger. What else do you think gravity might be dependent on? What else do you think gravity might depend on other than just the mass of the object? Okay, the height or the distance away from the object. Okay, as you get farther away, would gravity get bigger or smaller? Smaller. So this would be an inverse relationship here. As it turns out, it's an inverse squared. All right. Anything else you can think of that gravity might depend on?
Acceleration.
The acceleration is caused by gravity. Let me ask you this. Is gravity the same on the Earth as it would be on the Moon?
No.
Why?
Rotation.
The mass is, so it's not just the mass of the object that we're talking about, it's the mass of the planet or where you're on. Okay? So there's actually two masses here. Mass of the object and mass of the planet.
So is that like you multiply the two, you don't add or anything?
Yeah, they're multiplied together. All right. So Isaac Newton is the one that put together our formula for gravity. He's the one that described it really well the first time. And so this was pretty much what he said, that the force of gravity depends on the mass of the object, the mass of Earth, and the distance between those objects. But he wanted to write it as an equation, and so the way it is written is F equals, and he used a capital G, mass 1, mass 2, divided by d squared. G is just a constant. And Isaac Newton had no idea what the constant was.
Did you choose distance?
D is distance. If we're talking about the Earth, we can count it as the distance from the center of the Earth. So it's not going to be from the surface, but from the center of the Earth. Okay. So Isaac Newton said that this was the case. A lot of times you may see a negative sign here. The negative sign, all that means is the force is attracting. We'll get that a little bit more when we talk about the electrostatic force. But all the negative means is it's attracting. Sometimes you'll see it written there, sometimes not. When it's not written there, you just have to understand that the forces are pulling them together, not pushing them apart. Okay. Sometimes instead of D, they'll write the letter R. So sometimes instead of D, they use R, especially if you're talking about the orbit of planets, moons, things like that, because then it's a radius. So that's about as far as Isaac Newton went with this. And it wasn't until about 100 years later, an Englishman named Kavanaugh came up with a value for R, or not R, capital G. And capital G is 6.67 times 10 to the negative 11th Newton meter squared per kilogram squared. Okay, if you remember at the beginning of the school year, I said we're going to use all sorts of letters. We've used quite a few letters, and it makes a difference whether they're a capital or a lowercase. Okay, same thing here. Lowercase g is what? 9.8 meters per second squared. It's the acceleration due to gravity. The capital G is the gravitational constant, and it's 6.67 times 10 to the negative 11th Newton meter squared per kilogram squared. So let's do an example with this. Oh, by the way, the 10 to the negative 11th means what?
There's 10 zeros before the decimal.
Yeah, so that means 0.000000000667. 1, 2, 3, 4, 5, 6, 7, 8, 10. Yeah. Gravity is a very weak force. Gravity is a very, very weak force.
So there's only 6 zeros?
No, there's 10. Because we have, like, it only says 11 because we do remember the first number after the last zero.
Yeah, you move the decimal point 11 places over,
Because
which
that's the first
puts
number
you.
that's not zero.
All right. So gravity is a very, very weak force. So if it's a very, very weak force, how come gravity pulls so hard on things on the surface of the Earth?
Because of our Earth's mass.
The Earth's mass. The Earth is very, very big. The mass of the Earth is 5.98 times 10 to the 24th kilograms. It takes a lot of mass to provide a force that you can reasonably detect.
How many pounds would that be?
I don't know. Actually, that would be a little over 2 times 10 to the 24th pounds. Yep. All right, so let's go through an example here. We have 2 large elephants. One has a mass of 2,000 kilograms. The other has a mass of 2,700 kilograms. They stand 2 meters apart. What is the pull of gravity between them? All right. So we have several things here. We've got mass 1, that's 2,000 kilograms. We have mass 2, which is 2,700 kilograms. And then we have the distance, which is 2 meters. Our equation for the gravitational force is G m1 m2 divided by d squared. Yes. So we're going to fill in the values here. F equals G, which is 6.67 times 10 to the negative 11th Newton meter squared per kilogram squared. Times the first mass, 2,000 kilograms, times the second mass, 2,700 kilograms, divided by our 2 meters, and then we square it. Okay. One of the things you want to be real careful of when you're doing these calculations is how you put it in. So I'm going to go over it on the calculator. you'll want to do it the exact same way. So we need to put in our value of G. So you're going to put in 6.67. But the way you want to put the exponent in is you push the second button, the blue one, and then the comma where it has the double E above it. It'll just show one E on the screen, and then negative 11. You really want to do it this way instead of putting in times 10 to the power of the negative 11th. Because the calculator doesn't always do things in the order that you think they might be doing. It thinks those are separate numbers. All right, we multiply this by 2,000 and then by 2,700.
I can just use parentheses for all this until I put the times, right?
Yeah, you can do parentheses. And then we divide by our 2 squared. Don't forget to square the distance. And when you do that,
I get 9.0045 times 10 to the negative.
good.
Oh, I added up.
I pushed enter about the time you started talking. So yes. Okay, that's what you should have gotten. So our gravitational force here is 9.005 times 10 to the negative 5th newtons. So just to make sure that that's what we get, we have kilograms squared here on the bottom. That cancels with a kilogram here and a kilogram there. And then our meters get squared on the bottom of the fraction. So that cancels with the meter squared at the top. The only thing that's left is newtons. So if we wrote this not in scientific notation, gravitational force between these two large elephants is very, very small. Normally you don't need to do that. I wanted to do that here just to show, highlight.
Isn't it 0.0045?
Yeah, I just rounded it up 1. If you leave it as 4.5, that's fine. All right. So once again, our gravitational force, very, very small. The only reason it gets pretty large is because we have usually one of the masses, the Earth, that's very, very, very large. What we're going to do now... No. We're going to start talking about the acceleration, because a lot of times we're not just wanting to know the force of gravity, but we're wanting to know the acceleration caused by gravity. So anytime we've got a force acting on something, from Newton's second law, we know that the force is equal to the mass times the acceleration. And that kind of gives you the effect of what happens with the force. If that force happens to be gravity, then our gravitational force is G m1 m2 over d squared. Since this is the force and this is the effect of that force, we can put these together so that we have mass times acceleration, and this is the object, or let me call it m1 in this case, and that equals g m1 m2 over d squared. Well, we've got mass 1 on both sides of the equation. So those cancel out. And our acceleration is equal to g m2 over d squared. If we're talking about the Earth, then the mass of the Earth is 5.98 times 10 to the 24th kilograms. And the distance is the radius of the Earth for things that are on the surface. The radius, the radius of the Earth is 6.38 times 10 to the 6 meters. Make sure I got 8 correct. Yep. So let's put these numbers in here. So our acceleration is 6.67 times 10 to the negative 11th Newton meter squared per kilogram squared times the mass of the Earth, divided by our 6.38 times 10 to the 6 meters, and that gets squared. All right, before we start punching that into the calculator, what would you expect it to be? 9.8. Let's find out if it is. .67. Second e to the negative 11th times 5.98. Second e to the 24th divided by 6.38 times 10 to the 6 and squared. Don't forget to square the distance there. 9.8.